Okay, great. So last lecture we finished off solvers, iterative solvers. The screencast is not up on the website yet. It will be up today. So for those of you who missed class last time, you should be able to get to the slides, to the screencast later today. We spent most of the time, however, going over homework 2. So, and many of you who missed the class actually did very well on homework 2, so you didn't miss much. Secondly, I'm behind on a few emails from some of you, so I'll respond to you today. Questions specifically related to homework, I may not answer you directly unless the TA brings it up with me. So please email the TA, email 2450help@gmail.com, and try to go through, even if you have a question about the homework, or come see me here after class or office hours. Okay, do you have any questions about homework 3? So, yes.
With on number 1, you asked us to by hand solve 1 for n equals 4.
Yeah.
Is that the number of subintervals or the number of?
That's the number of points. So you'll have 3 intervals. And 2 of those points you actually know the temperature at, right? So you're really just solving for 2 points on the interior. Yeah. Yeah. And I have a follow-up for a couple questions. You had the time function in Python actually measures wall time, like I said last time, but I wasn't sure about that. And the other question you had was the matrix multiplication using the at symbol. And that's actually matrix multiplication in Python. So as long as the matrices are consistent in size, A at B is going to do a matrix multiplication. I don't know if you remember that question, but yeah. All right. Okay, so we're going to leave off the topic of linear solvers once and for all, but we're going to see them pretty much in every topic we're going to cover for the rest of the class, for the remainder of this class. The next topic is going to be interpolation. And does anyone know what interpolation is? Yes, yes. So what is interpolation?
So you have 2 points, and you know the value for those points, but you don't necessarily know what you need to know.
Yeah, somewhere in between. So all of you do interpolation all the time. So let's say, the temperature at 10 a.m. in Salt Lake was 64, and then at 11 a.m. it was probably 70. So what would the temperature be at 11:30 a.m.? You probably take the average of the 2, and that is interpolation. So we're going to cover interpolation in more depth in this series of lectures. It's a big topic. We're only going to touch the surface. But for the most part, you're going to be using built-in functions in MATLAB or Python to do interpolation for you. But we'll show you a few ideas of how it is done internally and how interpolation actually results in linear systems of equations. So that's why we started with linear systems of equations in this class. Okay, so the motivation, the concept is that you as engineers, as experimentalists, as scientists, as data scientists, you're going to be dealing with a ton of data. This, for example, is a set of data for the properties of air at atmospheric pressure, but at different temperatures. So on the first column, you have the temperature in Kelvin going all the way from 100 to 1,000 in increments of 50 degrees. So some experimentalists decided they want to measure the temperature, the properties of air at different temperatures. So they chose to take these temperatures, 100, 150, and so on, all the way to 1,000. Pardon me. And then measure the density of air given in this second column, the heat transfer coefficient, and the viscosity of air. So these are properties of air that you'll be dealing with. So when you're doing heat transfer with fluid flow, for example, with air, you're going to be needing the density, the heat transfer coefficient, and the viscosity. Now, obviously, these are a function of temperature. And oftentimes, you have this data as is, but you want to find a certain value, let's say the density, at 132 kelvins or at 746, right? So the density is going to fall between these 2 numbers, but how do you get that value? Okay? So that's kind of the motivation in general. We always have discrete data that we wanna interpolate. We wanna get a full picture of the data rather than just the values at these discrete points. And be careful, we are doing interpolation here. That means we're focused on finding values at points inside the bounds of the independent variable. So here, the independent variable is the temperature, going from 100 to 1,000. So you're allowed to ask to do interpolation for any value between 100 and 1,000. If you ask for the temperature at 1,500, that is going to be extrapolation, and that's very dangerous and scary. We're not gonna cover that. We're just going to cover interpolation. Interpolation is good because you are living within a set of data and you're just working inside that set of data. So it kind of makes sense. Interpolation also form the basis for numerical integration techniques and solving ordinary differential equations. So they're everywhere in numerical methods. The idea is simple, and that is like we said, like your colleague said, we pick 2 points, right? Let's say you want the temperature at 746. So you choose the points between you find the points that bracket 746, and then you can probably draw a straight line, or that's kind of the simplest thing you can do between 2 points. You draw a straight line, and then you find the equation for that straight line, and then you find the value that you are looking for, value of the density in this case at 746. But that's only that's kind of the simplest way of doing interpolation. It's called linear interpolation. But what if you want to get a bigger picture of this entire data set? You can fit a polynomial through this whole thing, or a cubic spline, and we're going to cover these ideas. Or you can bracket with, rather than just choosing 2 points, what if you think that the behavior of the density as a function of the temperature at different points actually is important? Like if you look at the beginning of the table, there's a huge change from 3.5 to 2.3 to 1.7, and then you go down very slowly, right? So what if I'm asking you for the temperature between 200, like at 231, you may want to include data at 100, 150, and then 300 and 350 to capture the trend a little bit better. And obviously, you cannot fit a straight line going through all of these points, because these points do not follow a straight line, obviously. So you're going to fit a polynomial, right? And we'll show you how we do that. Okay, now I'm going to start with linear interpolation, and to show you that you kind of already know how to do this, but we'll go through a simple example. So I picked 2 values from this table. These are given to us. 100 and 150 for the temperature and the corresponding densities. So if you think of these as pairs of x values and y values, in this case, the x values are 100 and 150. The y values are 3.55 and 2.33 for the density. And the question is, find the density at T equal 132 kelvins. Okay, so I'm going to put these data on a plot. On the x-axis, I have the temperature. At 100, we have the first data point, 3.5562. And then at 150, we have the second data point, 2.3364. And we're asked to find the temperature, the value of the density, that's kind of on the y-axis, for 132, shown by this black line over here. Okay. Now, the idea of linear interpolation and what you would do kind of immediately is to connect the points via a straight line and just kind of find the intersection of this red line with the vertical black line. And the process is very simple. The first thing you do is find the slope between these 2 points. So the slope is 2.34 minus 3.56 over 50. So rise over run, that's the slope. So you're finding kind of how far down are you going. If you go by 1 unit on the x-axis, how far down are you going to go on the y-axis? And the slope is minus 0.024, because we're going down, the density is decreasing. And then you find the value at 132 by starting at the point 3.56, right? And then you add this distance from here to here, 132 minus 100, that's 32, times the slope, right? So this is This distance is how much you ran on the x-axis, and if you multiply that by the slope, it's going to give you how much you're going to run or you're going to rise on the y-axis. And if you do this, you get an approximation for the density at 132. Now, the thing you want to consider is, the thing you want to think about is, make sure that this number is between the two values for the density, right? So if you had 3.55 and 2.33, if you end up with a number that's 7, obviously you made a mistake, because the value needs to be in between the two bracketing values for the density, okay? So let's generalize this, formalize it, and show how we end up with a linear system of equations in this case. So what we just described is two pairs of data, x1, y1, and x2, y2. This was temperature, and density. We'll just call them xi. Okay, so you are typically given data as xi's and yi's. It can be temperature, density, temperature, viscosity, whatever. Okay. The question is to find y of x for any value of x between x1 and x2. We're going to fit a straight line. What is the equation for a straight line? This is where we're going to start. The equation for a straight line is y equal mx plus b. Okay, and I put m and b in red because it is these values that we don't know. We want to find the slope and the intercept for this straight line, and then we have a definition of what the straight line is. Then once we know m and b, we can plug in any value for x and find what y is. So how do we do this? We have m and b, they are two unknowns, right? So how many equations do you need? Yeah, you need two equations to solve for these two unknowns. And so where do we get these two equations? From what? Yeah, from the given data. We have two sets of data, right? y1, x1, and x2, x1, y1, x2, y2. So, and we know that this line needs to pass by these two data points. So what we do, we evaluate this line at these data points. So we know we want the straight line to pass through x1, y1. Therefore, that data pair needs to satisfy the equation for the line. So that y1 is mx1 plus b. And same thing for the other data pair. y2 is equal mx2 plus b. Now again, the symbols in red are unknowns. Do you agree? We don't know those, but we know y1 and x1 and y2 and x2. So then you have a linear system of equations right here. So can you see how we can write this in matrix form? So this kind of flips all the nomenclature on its head. In the past, previously we used to write, A11, A12, etc. in the matrix, in the coefficient matrix, and then in the column, in the unknown vectors, we had x1, x2, x3, and so on. And then on the right-hand side, we had a bunch of values. Over here, we have the x values in the coefficient matrix. Why? Because we know these data. Remember, ax equal b. A is the coefficient matrix that we know. B is the right-hand side that we know. X is the vector of unknowns. In this case, the vector of unknowns is m and b, is the vector mb. Okay? So then we can just simply invert this system of equations, which is pretty simple, and we get this simple solution for any 2 points. Given any 2 points, this is the solution for linear interpolation. You've probably done this in class somewhere in your school, but what this is saying is, so the slope is y2 minus y1 over x2 minus x1 times x. Okay, so that's obviously kind of the slope. We kind of knew this from the beginning, right? And then x1 and y1 are known. x1, y1, y2, x2 are all known. You're only left with the value of x, which is where you want to evaluate the new quantity, and y is the value at x. So then, in this case, you want to plug in, you want to find the density at 132. You put 132 here where x is, and then you find that's going to give you the density, the interpolated density between these 2 points and it's going to fit somewhere on this line. Okay, pretty simple. You can program this into your calculator. Very simple. The advantage of this is that it's pretty much easy, very easy to implement and easy to use. For your homework, you're doing kind of back of the envelope calculations, and it's very fast and efficient. The disadvantage, main disadvantage, is that it may not work well if the data is inherently nonlinear or if you have very sparse data. So let's say the density and temperature, the density is a function of temperature, so we know it kind of behaves with exponential decay. If you don't have a lot of points to represent that data, then linear interpolation is not going to do a good job. Okay? So let me show you this plot, actually. This is a plot of the density versus temperature. So I'm taking the first column on the x-axis and the second column on the y-axis. And you see there's kind of this behavior, this exponential decay behavior. Now, of course, you can do linear interpolation between each and every pair of points, right? You can take the first 2 points and draw a line, connect the other 2 with a line. That's kind of the most straightforward thing you can do. And this is what you get when you get this, when you do this. Obviously, there's not a lot of data over here, so linear interpolation may cause some error, may be a little bit inaccurate, but over here, yeah, definitely use linear interpolation. Or if you had a lot of data everywhere, I would automatically use linear interpolation. That's kind of the simplest and easiest option to try at first. So you can apply linear interpolation for any 2 pair of points, okay? Or you can take a collection of points and start the first pair, the second pair, etc., and connect them with a straight line. Okay? In practice, what you need is just, ask yourself, where am I trying to calculate the value? Find the 2 bracketing points and do the interpolation. And it's very easy to do in Python, and I'll show you how we'll program this. Okay? In Python, there's a function in NumPy called interp, okay? And it takes 3 arguments, xi, xi, and yi. Xi and yi are your input data, okay? So these would be a vector of temperatures and a vector of values, densities, for example, in this case, okay? Xe is the value or a vector of values at which you want to evaluate your function, at which you want to interpolate. So in this case, this would be 132. And ye is the value that is returned by that interpolation. Yes?
Does this function require that x is between xi and xy, or xi or the 2 distances, I guess?
Distances?
Like, does xe must be contained in xi?
Yes. I mean, it can try. It's not a requirement. It may throw an error. It's a good question, but I wouldn't use it outside. I mean, even if it doesn't throw an error, I wouldn't trust data, extrapolated data, okay? But your xi and yi, at a minimum, needs to be a vector of 2, right? Because you need 2 points at least to do a linear interpolation. But you can give it an entire data set, okay? You can give it the entire data set, like the temperature and density, and you can ask it to just give you one value, to return the density at one of the temperatures. And it will find the correct interval, and then it will return the value for you, okay? Now, what if you wanted a smoother interpolant? So let's say, you're not satisfied with connecting things via a straight line. What if you want to connect them, in a smoother fashion? They look like a polynomial or a curve. Okay, so let's start by observing something. For 2 points, we were able to connect a straight line with the equation a0 plus a1x, right? So that's mx plus b, okay? But what if you chose 3 points to interpolate the data? So I wanted temperature density at 132, and I want to pick temperatures 100, 150, and 200. Yes, you can fit a quadratic in 3 points. So remember here, the unknowns are the coefficients, right? And the number of unknowns is going to correspond to the number of points, okay? So for 3 data points, you can fit a quadratic, and a quadratic is, the x squared polynomial, so a polynomial of order 2, but it has 3 unknowns because there's this a0, and then a1 and a2. So with 3 points, you can fit a quadratic polynomial. With 4 points, you can fit a cubic polynomial, right? Because you have 4 points, and a cubic polynomial has 1, 2, 3, 4 unknowns. So remember, number of points is gonna help us find equations for the unknowns, okay? And where do the unknowns come from? So you have 4 points. You want the polynomial to go through these 4 points. So you want to satisfy the polynomial at point 1, point 2, point 3, point 4. So that gives you these 4 equations. And in general, if you have n plus 1 points, you can fit an nth order polynomial with these n plus 1 points. Yes?
This is gonna be like, you do like, let's say 100. That's gonna be pretty intensive.
It's going to be intensive, and we're going to show that it doesn't work very well. So you're talking. So for 100 points, you have a polynomial of order 99, and that polynomial has 99 roots, and so it is going to go up and down and up and down, and it may. So between 2 data points, it may go up and behave very erratically, and we'll show this through an example. But the idea, the concept is that if you're given n plus 1 points, you can fit an nth order polynomial. Okay, so for 3 points, you can fit a second order polynomial. For 5 points, you can fit a fourth order polynomial that goes through these points. So you make sure that you are actually satisfying the given data. So if we fit a polynomial, so let's say what we had 20 data points with the temperature density. So that's going to fit a polynomial of order 19. That polynomial is going to go through all the values for the temperature and density. So 100, 150, 200 is going to return the correct values that you got from the experiment. But in between, it may not behave well, and we'll see how that works. So anyway, this is a formalization of this idea now that we can fit a polynomial through any part or the entire data set. So you can choose these 3 points and fit a quadratic. Even if you want the temperature here, the density at this temperature, you may say, these 2 points are not enough. I want to see the trend here and here. So you choose these 4 points, and then you can fit a cubic polynomial with these 4 points, right? So you are free to do that. Or you can just fit a polynomial through the entire data set and say, you know what, I don't want to bother about picking and choosing which interval of points that we want to evaluate at. Let's just fit a polynomial through the entire data and just ask that polynomial, evaluate it at whatever value you want. Okay? So how does this work? The one condition is that the polynomial must pass through each and every point that you are given. Okay? So how do we formulate this? Again, the unknowns are the coefficients for the polynomial. For n plus 1 data points, okay, we have n plus 1 unknowns. Okay? So we need n plus 1 equations. And therefore, we need we have n plus 1 points. So what do? We just evaluate the polynomial at each and every point. So at most, for n plus 1 data points, we can fit a polynomial of order n. Fix that in your mind, because you're gonna be asked about this in homework and in exams. Okay? For n plus 1 data points, you can at most fit an nth order polynomial. And if you don't want to memorize it, I don't want you to memorize it, actually. I want you to kind of think about it critically. In this polynomial, we're looking for the unknowns. The coefficients are the unknowns, a0, a1, a2, all the way to an. So that tells you how many points you need. Okay? And that tells you the order of the polynomial. So I'll give you an example how we can solve for these coefficients now. We're going to do the same thing we did for the linear interpolation. So let's say you're given this data, x1, x2, x3, and y1, y2, y3. So we have 3 data points. What order polynomial can we fit? 2. We can fit a quadratic. So the equation for our fit is a naught plus a1x plus a2x squared. A naught, a1, a2 are the unknowns. Okay, so how do we get the three equations for the three unknowns? We evaluate at the 3 points. At y1, at y1, we take the polynomial a naught plus a1 x1 plus a2 x2, right? Because y1 corresponds to x1. And then at the second point, y2 is a naught plus a1 x2 plus a2 x2 squared. And same thing for y3. Okay, so now with these guys, now we can construct a system of equations. So what are we going to have in the coefficient matrix? The x's, right? Because those are the known values, right? And the column, the unknown column vector are the coefficients contains the coefficients for the polynomial, and on the right-hand side you have the values, the y values. And if you're still kind of confused about this, just do the matrix vector multiplication here. The first equation is 1 times a naught plus x1 times a1 plus x1 squared times a2 equal y0. That's equal y1. Sorry, so this should be, this should be y0, y1. This should be y0, y1, y2. Okay, so there's a small typo here. But you get the idea, okay? Does anyone not agree with this? Okay, so always ask yourself, what do I know? What values do you know? And what values you don't know? What are you solving for? You're not always solving for x. We use x as a dummy variable because, it's just kind of, we inherited that through centuries of this nomenclature. But don't be confused that x is not always the unknown, right? In this case, the x values are given to you. In this case, the unknowns are the coefficients of the polynomial, the a values, okay? And so in general, if you write a polynomial using this summation, so that's a naught plus a1x plus a2x squared and so on and so forth, and you are given n plus 1 data points. So remember, these data points are pairs, x1, y1, x2, y2, x3, y3, and so on. This is the system of equations that you will get in general. Okay, you see the pattern. Ones on the first column, the value of data on the second column, the values of the squares of the x data on the third column, and so on, all the way to the nth power. Okay. Now, what is the size of this matrix? Yes. So what is the size of this matrix? So we have n plus 1 unknowns, correct? Those are the a0 to an. So if you count from 0 to n, that's n plus 1 values. So the matrix, what is the size of this matrix? It's n plus 1 by n plus 1. Okay? And then given the xi's and yi's, you solve this system of equations to find the coefficients. This is like one of the simplest applications of where you find linear systems, where you end up with linear systems of equations. This is a system that is very, very dense, okay? And you probably want to use one of the built-in methods in Python or MATLAB, okay, to solve it. In practice and in Python, when you code things like this, so we're going to do an exercise to show you how we can find the coefficients ourselves, but we'll also learn how to use a function in Python that's called polyfit. And the polyfit function works in 2 steps. First, you give it the data, the x and the y, the xi's and the yi's, and say, hey, do a polyfit, and you give it the number, the order for the polynomial, okay? Which you can get from the size of the data, right? And then what it does, it solves this system of equations, or a similar system, and returns the coefficients. So the return value of the polyfit is just the vector of coefficients. And then the second step is use another function called polyval, which takes a vector of coefficients and evaluates those, uses those to construct a polynomial, and find the value that you're interested in. And it looks like this. So first step, you import polyfit and polyval from NumPy. And then you are given xi, assume you're given xi and yi, which you will, right? And then you do a polyfit on xi and yi and store that in P or in coef, call it whatever you like. Remember, that's a vector of coefficients. So this is the solution. These are the coefficients that will construct the polynomial for you, a0, a1, and so on and so forth. Okay? Now you see xi and yi, I describe them here, independent variable, dependent variable, known data. And there is this n at the end. You may say, okay, so if we can only fit, if we have n plus 1 data points and we can only create an nth order polynomial, why is Python asking us to specify the order? Because you can have 100 points and you can put 2 over here. The reason is that polyfit is a very general function that doesn't only do data fitting and interpolation, it does something called regression, which we will learn next. Okay? So it can fit a second order polynomial through 100 data points, but it will not go through the data points. This is called regression. We will talk about this after we finish with interpolation. But for the purposes of these lectures of interpolation, n is always the expected order of the polynomial. So if your array size, if the data you're bringing in is n plus 1 points, then you have n. Or if you're bringing in 100 points, you put 99 in there. And that is going to give you the correct size polynomial. Okay? Now that you have the coefficients, you need to construct the polynomial. You need to do a0 plus a1x squared and plus a2 plus a1x plus a2x squared and so on, and evaluate the polynomial at the value you're interested in. You do this with another function called polyval. And polyval takes a vector of coefficients for the polynomial and a vector of data at which you want to evaluate the polynomial. So again, this could be the 132 degree K, right, that we're interested in, or a bunch of temperatures, 132, 164, 746. And it will automatically evaluate the polynomial, do the interpolation for you, and store those in YE. Those are the interpolated values. Okay? So let's go ahead and do this exercise in class. We're going to use polyfit and interp. Okay? Let's see. And I'm going to turn. Any questions so far? Okay. I'm assuming everything is clear. So I am going to create a Jupyter notebook here. Okay, I'm going to create a Jupyter notebook. And I am going to import a bunch of things first. So import NumPy as MP, import matplotlib.pyplot as PLT. So usual stuff. And then from NumPy, import polyfit and polyval and interp. Okay? So remember, interp does the linear interpolation. You give it 2 points. And we'll start with that one. All right? So first, let's do some linear interpolation example. Okay, so the given data, given the following data for temperature and density, find the density at 132 K. Actually, yeah, at 132 K and 890 K. Okay. So I'm going to pick the data from the array from the, where is it? Just get to my slides. And okay. So the data are, so we have t equal, what is it? So, okay, which values do we want to do 132 and 890? So let's look at the slides again, at the table. 1 second, please. Okay, so this is the table. We want to evaluate the density at 132. So we want these two pairs of points, 100 and 3.5562, and then 150 and 2.3346. So let's enter those. I'm going to create vector of xi and p dot array. I'm going to use NumPy arrays all the time from now on. So the x values are 100 and 150, right? Because we want to evaluate at 132, so we want the 2 points that bracket this 132. Okay, and then yi are the density at those values, or this is given to you. Again, a NumPy array, 3.5562, and then 2.3364. All right. Okay. Okay. So now, okay, how does interp work? So interp, if you forgot, you just type interp, open parentheses, and press Shift-Tab, and it gives you a description of what the function takes. So it takes x, xp, fp, and a bunch of optional values. So let's focus on these three guys. X is the value at which you want to interpolate, or a vector of values at which you want to interpolate. And xp and fp are the known values, okay? So very simply, we can do, in this case, our x, or at which the value at which we want to interpolate, is 132, and the input data are xi and yi. And this gives us, you know, row 132 equal, and then let's print it. Row at 132k is equal row 132. Look at that. It automatically did the interpolation for you. You can compare that to the value we calculated on in the slides. We did a lot of round off, you know, with our calculation, so the numbers are going to be a little bit off. But the first thing you ask yourself is, does this value fall between these two? Yes, absolutely. So good, great. So how about, you know, the value of 100? What do you expect to get at 100? We get what, which one? Yeah. Row 3.5562, absolutely, because it needs to pass through that point, correct? And same thing for 150. And you can also give it a bunch of temperatures that you want to find, you want to interpolate at. So let's say you want to interpolate at 110, 132, and 148. Okay? So you can give it this vector, and look at that. It did the interpolation for you. So this would be the density at 110, density at 132, density at 148. Pretty easy. Okay? So now let's try with polyfit. Actually, before polyfit, I want to show you how we can do the entire data set also with linear interpolation. Okay. So the entire data set is given. I already kind of programmed this already. So the range for temperatures goes from 100 to 1,000, okay? And I'm going to create this range by, pardon me, calling the NumPy arange function, and that is going to return an array of temperatures going from 100 to 1,000 in increments of 50. And if you want to double check that, just print the value, and then you see our temperatures, 100, 150, 200, etc. And then this is where I input manually the values for the density. And this is just a plot of what the density looks like as a function of the temperature. Now, here's this is what's so cool about the interp function, is that we can give it this entire data set, and it would create an interpolant for you, and then you can find, you don't need to bracket like we did previously. You just give it any value for temperature, and it will find the correct bracket for you. So rather than using xi and yi, the bracketed values, okay, I'm going to use the entire data set. So I'm going to say row, my new row, is equal is equal interp, and let's ask the interpolant to find the value at 132. But I'm going to give it the entire data set. What is our xi's in this case? It's t, correct? And what are our yi's? They're the row values. So t and row. So we're giving it the entire data set, and we're just asking it to find the density at 132. Then print row. Look at that. What's great about this now is that I can request an interpolation at a bunch of points that are not limited to the interval we chose. So like here, 100, 150, we were limited to choosing data in between that interval. Now we are limited by the entire data set. So I want to evaluate the temperature, the density at 132, so np.array. So 132 and 890. And then I can ask the interp function to do an interpolation of t and row to the values at specified in tt. There you go. This would be the density at 132, and this would be the density at 890. So let's look at the original table to make sure that this value makes sense. We had 0.391, and 890, that's between 850 and 900. So between 0.4 and between 0.38 and 0.409, which is great. That's a good value. Okay? Any questions? That's the interp function. Okay, so now let's move on to polyfit, and let's start with a quadratic polynomial. Let's say, it wasn't 2 points were not enough. We want to use 3 points. So we'll start with the same thing. We'll just pick 3 points, do a polyfit, evaluate the temperature, and then try to fit the entire data and see how we get into trouble. It is good to get in trouble and make mistakes, because that's how you learn, really. If everything worked right out of the box, there's not much learning value in things. All right, so let's go to polyfit. Okay, so now I'm gonna again request the temperature at 132, but we're gonna use 3 points: 100, 150, and 200. Okay, because those are the only points available to us. So then our xi's, or if you want ti's, just to kind of confuse you a little bit. So we have 100, 150, and 200. And then the values for the density at those temperatures, p.array, we had, what, 3 point, what is it? It's those first 3 values. Okay. Let me just clean it up a little bit. Okay. So now we're going to follow what the suggestion was for polyfit. And where was that? Okay. So first, we do a polyfit for the known data, the xi's and the yi's, and we'll specify the order. We want to make sure that if we have n data points, that's going to be n minus 1, the order. Okay? And then we'll store those in P, which is a vector of coefficients. Okay, so I'm going to call this coefs equal polyfit. And again, if you're confused about polyfit, just type Shift Tab, and you get these descriptions, x, y, and degree, which is the order of the degree of the polynomial. So in this case, we're going to give it ti, rho I, and what is the order? So in this case, the order is going to be 2, because we have 3 data points. Okay? Or you can just simply define the order, or P order equal len of the input data minus 1. Okay? P order. So now, if we solve this for this, it's just going to give us a bunch of coefs. Okay? So these are the coefficients of the polynomial. This is actually A0, and this is A1, and this is A2. This is the result of solving the system of equations that we discussed earlier. So now to compute a value, we need to use these coefficients in an actual polynomial, A0 plus A1x plus A2x squared. So then we use the polyval. Okay? And for this, we do rho is equal to polyval. And what is polyval request? It requests a list of coefficients, P, which is described here, P0, x to the n minus 1, etc., and a value x at which you want to evaluate the polynomial. Okay, so then we're going to give it coefs. Correct? Is this clear so far? And then the value at which we want to interpolate, which is 132. And then print rho. See what happens. Okay, so that's what it gave us, 2.7. Now compare that to the linear interpolation, 2.77. There's a difference. Yes?
Well, polyval use a list of points, like, so could you put TT instead of 132?
Yes, of course. So like linear, so what your colleague is asking, and you're kind of getting ahead of us, he's asking if rather than evaluating at one value, can we evaluate a bunch of values? Yes, of course. But it is highly recommended that those values be within the interval that you've chosen. So between, our interval was between 100 and 200. So we can use this TT that we declared before. So I'm going to declare it again here for sanity. Okay, so TT. Then we do TT. Ta-da. There you go. So if TT was, what is it? 110, 132, 148. This is the density at 110, density at 132, density at 148. And you can actually go and plot, create a plot for how this polynomial looks like. Let's actually do that. So we had the given data to us, which looked like this. And then we created a polynomial that was a quadratic, and we knew this polynomial only passed through these 3 points. But then we can continue plotting this polynomial and see how it behaves beyond these 2 points. Is it going to go up or go down? Is it going to pass through these other points? So let's just go ahead and see that. So first, I'm going to do a plt.plot the original data, which was t and rho. T and rho. And then again, I'm going to evaluate polyval at, so given the coefs, I also want to evaluate it at t. So rather, I want to evaluate it at the entire data set and see what it does. So let's see what happens. Coefs. Look at that. So the original data, let's plot it in stars. So black disks maybe, and then this guy. Yeah. So this is our original data, the black circles. And this is our quadratic polynomial that only went through the 3 points. We wouldn't expect it to cover any of the other data. Of course not, right? Because we only fitted the first 3 points. It looks pretty close to the 4th point, but that's still extrapolation. So that's why it's a bad idea to do extrapolation. Okay? So now, let's ask ourselves then, okay, let's fit a polynomial through the entire data set and see if it actually goes through it. Okay? So let's do that. For this, what we're going to need is, again, coefs. We do polyfit for what? We want to do polyfit for, let's say 132, but we want to fit it over the entire data. And those are the t's and, sorry, my mistake. Polyfit for the entire data. This is the incoming temperature, the entire temperature, this T over here, and the entire density. Okay? And then rho. And then what is the order? What is the polynomial order? So if you have n data points, the order needs to be n minus 1. Okay? So how do we get the order? That's length of temperature. So that's the size of the input array, n data points minus 1. We can do the length of row, absolutely. So when you run this, look at this. It gives you a warning or an error. It says polyfit may be poorly conditioned in this case. So let's keep that in mind and see what is going on here. And then I'll explain to you why it's a bad idea to fit a high order polynomial. Okay? So I wouldn't go more than 5 or something, or a fourth order polynomial. So let's go ahead and evaluate this and say we want to evaluate, let's evaluate it at 132. So polyval 132 given, polyval coefs, it takes the coefs first. So these are the coefficients that we just computed. And I want to evaluate this at 132. If you print it, it gives you 2.8, a value of 2.8. We had 2.7 previously. So obviously something is going on here. Okay, but what about 890? What was so special about 890? Let's evaluate the density at 890. Okay, obviously that worked. What about 910? Okay, so obviously that worked too. What about 980? Oh, look at that. Can you have a negative density? Of course not. So something unphysical happened here. Something wrong happened. So the polynomial, while it fit the points, 800, 900, 1,000, so if we ask it for 1,000, it's going to go back to the true value, 1,000.34, but then at, what was it, 980, it was negative. So what's going on? Let's plot it. Let's do a plot. So plt.plot. Again, I'm going to plot t and rho, the initial, the input, the incoming data, and then we're going to plot t, and then polyval coefs at t. At t, what happens here? Well, obviously the polynomial is going to go through every point, right? So the polynomial does indeed fit every point. But what I haven't plotted here is, what does the polynomial do in between? So let's create a linear space going from 100 to 1,000 with data not only at 100, 150, 200. I want data all the way 100, 110, 120, and so on. So for this, we're just going to create a linear space. TT is mp.lin space from 100 to 1,000. This is the temperature range, and I'm going to put 100 points in those. And then I'm going to evaluate my new polynomial at TT and plot it. Let's see what happens. Look at that. So this is giving you, remember the polynomial that we created is a continuous polynomial. You can evaluate it anywhere in between your data, whether it makes sense or not. So this is what I did here. I took that polynomial, which is just a function of x for all you care, right? And you're just going to evaluate it at all of these values for x, and look at the behavior of the polynomial. Look what happens here. It dips somewhere between like 900 and 1,000. It takes a negative dip and then goes back up. The yes.
Where would that error come from? Because this is basically a Taylor approximation, right?
It's not, well, if the data is not inherently polynomial, you may be overfitting the data, in this case. And you can't, the higher the order of the polynomial, it's not like a full Taylor series approximation. It's just saying, hey, I want to fit a polynomial. There's a theorem in math that says the real space is dense with polynomials. So you can put a polynomial in any set of data. But the problem is the higher the order the polynomial is, the more roots it has, so the more oscillations it's going to have. And so, it's a bad idea to fit polynomials with, large data sets. That's the lesson you learn here. Yes. Did you have a question? No. Any question over there? Yes.
Can you use interpolation large data points?
We just did. Yeah. So with the interp, so let me plot the linear interp. I'm going to do TT and then interp. And what did we do? What did we need for interp? Again, TT, the vector of values at which we want to interpolate, and then T and row, and then use red disks for that. Yeah. So linear interpolation is way better. Look at that. Linear interpolation kind of goes through the entire original data. Yeah. If your data is dense, if you have a lot of data, you have finely resolved data, linear interpolation does pretty good. Okay? Okay. So now I'm going to discuss cubic splines. Actually, before I leave this topic, let me show you how we can solve for these for the coefficients ourselves. So that was the last piece we did not finish here. Okay, so this was the general formula for finding the coefficients of a given n data points or n plus 1 data points. You want to build an nth order polynomial. You want to look for you want to find the coefficients. This is what the linear system looks like. You are given the xi's and the yi's. You want to find the a values. And so how do we construct this, this system of equations in Python? So let's go back here, and I'm just going to start with these 3 data points because they're easier to look at. Okay, so first thing, I want to create an array. So first, let's get the length, len ti. So that is obviously 3 in this case. And now I'm going to create a matrix. And remember, in NumPy arrays, we're not going to call NumPy matrix. Don't use that. Just use NumPy arrays and use nested lists in that. Okay. So in this case, I'm going to create a 2-dimensional NumPy array, np.zeros. It's just filled with zeros. And it is of size n by n. Okay? That's the original size of the data. Correct? So, and if you print this, print A, it's just 3 by 3. But it has zeros in it. Okay? So now we want to fill this array. The first column, we want to fill it with 1s. The second column, we want to fill it with the x values. The third column, we want to fill it with the square of the x values. So what I'm going to do, I'm going to loop over the range of, yes, so let's loop over the number of unknowns that we have. So for I in range from 0 to n, so that is going to go 0, 1, 2. Okay? And those are actually the exponents of the first, second, and third column. Okay? So now how do you access a full column for a matrix? So remember last time we used the semicolon to kind of index through an array. Okay? This one is the same thing, but you now have 2 indices. To access a value in an array, before we do the loop, let me just show you how you access a value in an array. You need 2 indices. So this is indexed as aij. So a00 is going to be this first entry over here. Okay? So let me show you. If we set a00 to 33, it's going to put 33 here. If we do A 1, 2. So that is the first row, the second column equal 12. 1, 2, print A. This is what's going to happen. 12, right? Okay. So A, row 1, column 2. Okay, so this is how you access an array, a two-dimensional array. So you have two indices. But what if you want an entire row? What if I want, okay, so let's leave A here as is. What if I want the entire first row? What if I want this entire thing? So here's how you do it. You use the column notation we introduced in class last time for the semicolon. So for the first row, we're gonna request the entire row. So you just put these two dots and then comma. You give it the index. So sorry, A row 1. That is gonna give you. Okay, sorry. It's gonna give you. Oops, sorry. Okay, so if you want the first row, so let's print A. Okay. Sorry about the confusion. Reset everything, start from here. So this is what A looks like. To access the first row, now remember the indexing is row, column, okay? If I want the entire first row, all I need to do is ask the array, give me this row, but everything in terms of columns, all the columns on this row. So then it returns 3300. Okay? If instead you want to access the first column, you swap that notation. Okay? They're going to look the same. So if you swap this notation, it's going to give you the first column. Okay? So we're going to use this to fill this array with 1s and x's and x squared, etc. How do we do this? We said we want in our first column, we want it to have 1s. So that's going to be np.1s n. For the second column, which is indexed as 1, we said we want to have xi, right? So the values of x. So what is that? That's just simply ti. And for the last column, we said we wanted to have the square of the input value, so that's ti squared. So now if I print A, this is what we're going to get. You're going to get 1s in the first column, the values of the temperature, or T, for the second column. So that's 100, 150, 200. And then the squares of these values here. To do it more generally for any data, you just need to do a for loop. And the way you do this is, rather than doing these hectic statements, you just go do a for loop for I in range 0 to n. These are the number of unknowns, okay? Then the size of the matrix. And then simply say A, give me the ith column, and in the ith column, put ti to the power I. So as I starts at 0, that gives you the first column. We have 1s in it, which is ti to the power 0. That's going to be 1s. For the first column, the second column, I is going to be 1, and that's going to give you ti to the 1, so that's going to give you the ti's. Okay, so if you print A now, it's going to look the same thing. Okay? And that's it, really. All we have to do now is solve what system of equations? A and B. So if we use the NumPy linear algebra library, so solution is equal numpy.linalgebra.solve. What are we going to give it? We're going to give it A. And what's on the right-hand side? No, row I, right? Because those are the values. T is the independent variable. Row is the dependent variable. So row I, rho I. So that gives us the coefficients. And then I'm going to print the coefficients and compare them. Okay, so this is what you get. 7.8 for A naught, minus 5.58 times 10 to the minus 2 for A1, and so on. You get 3 coefficients. Okay, so let's compare this to what polyval does. Okay, so we expect polyval to give us the same thing. So if we do coef or P coefs from polyval is equal polyval and polyfit. Polyfit. We are fitting. We are finding the coefficients of the polynomial for what? What are the xi's? Ti, and then rho I. And what is the degree of the polynomial? It's n minus 1. And then I'm going to print P coefs. Now look at that. They're the same, except Python returns them in reverse order. So these two guys are the same, these two guys are the same, these two guys are the same. So we are actually doing what Python is doing. All right? Any questions? Okay. Now I'll switch back to my slides. And show you one last type of fit, which is cubic splines. So again, like I said, we can use different data points to do interpolations. That's the best way. I wouldn't go above a third order or a fourth order polynomial, you know. Anyway, the last topic we want to cover are cubic spline interpolations. Who's heard of splines, cubic splines? Yeah, so, you know, the way they work is that because we know cubic polynomials are kind of nice and they fit data very nicely, the idea is, given a set of data, so let's say you have 4 data points over here, this guy, this guy, this guy, and the other guy. The idea is to fit a cubic polynomial between every 2 data points. Now you may say this doesn't make sense because we only have data points. Well, we're going to create a bunch of conditions. We're going to come up with a bunch of conditions to make sure we have enough equations to solve for the unknowns. So the idea is you fit a cubic polynomial in this guy, cubic polynomial between these 2 points, and a cubic polynomial between the other 3. So with 4 data points, you have 3 cubic polynomials, okay? Or with n data points, you have n minus 1 cubic polynomials, or for n plus 1 data points, you have n cubic polynomials. But how many unknowns per polynomial? Cubic polynomial has A1, B1, C1, A, B, C, and D, has 4 unknowns. So each cubic polynomial has 4 unknowns, right? For the quadratic, we had 3 unknowns. For a linear, we had 2 unknowns, right? For the cubic polynomial, we have 4 unknowns. So in total, if we have n polynomials, so n plus 1 data, you have n polynomials. 4 data points, we have 3 polynomials. And 4 unknowns per polynomial, so that gives you a 4n unknowns. So we need 4n equations. So how do we come up with these equations? Well, the first constraint is to say that at each interior point, okay, so at each interior point, so these 2 points, we must match the given data for each of these polynomials. So this polynomial needs to match the data here, and that polynomial needs to match the data here. This polynomial needs to match data here, and that one needs to match the data here. So that gives you 2 times n minus 1 constraints. Try to think about it at home, you know, how these the number of constraints comes about. Then the other condition, so we have only 2 n minus 1 constraints now. The other condition, is that at each point, at each of the interior points, we need to make sure that the first derivatives of the polynomials match. So the first derivative of this guy equals to the first derivative of that guy. That gives you 1 constraint. in this case, and the first derivative of this guy matches the first derivative of the other guy. Of course, because you want them to be continuous, right? You want the slopes to be the same. So that gives you n minus 1 constraints. Then we can do the same for the second derivative, also at the interior points. Okay, so now we have 4n times 4n minus 1 constraints. Okay, so we need 2 more, so that's 4n minus 4. So we need, 4 more constraints to get to 4n. The first and last splines must pass through the first and last points, obviously. So that gives you 2 constraints. And then the second derivative at the first and last points, so the first and last polynomial, the second derivative needs to be specified. We usually set it to 0. Okay? So that in total gives you 4n constraints. And you can kind of construct all of those by hand and go through the math. It gets pretty complicated. But the great thing about polynomials is that it gives you a really nice, smooth interpolant. It is more accurate than linear interpolation and doesn't get wiggly like cubic, like a 50th order polynomial, right? Because you're only working with third order polynomials, right? So they're kind of nice and smooth. They do nicely, and they're only, you fit 1 cubic polynomial per 2 points, right? And so they're really nice. The problem is that they require a little bit more work, but you know what? Most packages like Python and MATLAB, they have built-in cubic spline features, so you know they're very easy to use. Highly recommended. And in Python, this is how you invoke the cubic spline. So I'll give you these recipes in your homework just to see how they work. Next time, we'll finish off where we left off here. We'll give a few examples and compare splines and polynomials, and then we will start with regression next Thursday.